De Broglie, you know De Broglie hypothesis. His thesis was few pages, like around 27 or some pages. And when he was doing his PhD, uh, H it is equal, H over P equals lambda or P equals H over lambda. It is called de Broglie hypothesis. You know, hypothesis is the thinking of someone. And when it is in the form of some derived equation, you call it a theory. And when that theory is experimentally proved, then it becomes a law. So it was in the very early stage hypothesis. And the that time Dean of Sciences was Peter Debye. You know about Peter Debye. Peter Debye was uh, an arrogant person, and you can understand his level, the Peter Debye. He objected on Einstein's concept in a couple of matters, and at the end, Peter Debye was right while Einstein wasn't. So he was of that level. Schrödinger was the examiner of this thesis of de Broglie. So Peter Debye said to Schrödinger that now we will be awarding degrees on hypothesis. This is not a joke. So reject his work. This is not suitable for a PhD degree. But he was an expert in the field. He knew the things, and he actually remained unable to reject this work. Because I have explained in the quantum lectures, there you can see in the introduction in many details that what was the bridge that de Broglie provided between the wave and the particle nature. So he said that this is right, the work is okay. And then Peter Debye told Schrödinger that now you will have to provide the formulation. And he stayed in Switzerland for 2 more weeks after the exam, writing one equation after the other, and he was not finding any clue. But when he just started from the energy conservation equation, E t plus V, he wrote his very first equation, H psi equals E psi. Hamiltonian is kinetic energy plus potential energy is equal to total energy. This is a wave function. And then he formulated the quantum mechanics. So it was just as a result of that thing. So here, from all this, this is the mechanics of the tiniest particle. When they become tiny particles, then the wave nature and the particle nature overlap. The switching in or switching over will cause you the uncertainty in some measurements. And this is currently being a very fundamental mechanics, but there is a big difference between the classical mechanics and the quantum mechanics. Classical mechanics is realistic, while quantum mechanics is probabilistic. You will talk in terms of probability. Like we said, when Musa converts into a wave, he's so tiny that we cannot differentiate. Then you cannot say exactly here. You will say Musa is probable in this region, and you will find the probability. Somewhere it will be more, somewhere it will be less. Like you say that electron in the hydrogen orbit is going in this orbit, and the radius of the orbit is this one. It is actually the line on which you are having the maximum probability, because the electron is here as well and here as well, but the probability is less. It is like a Gaussian distribution. Its maximum is there. So it's kind of a blurry orbit. Maximum probability is here. So that's why we say that this is the orbit. So it is in terms of probability. It is not realistic. It is probabilistic. And due to that reason, Einstein once said that God doesn't play dice. That This is a mechanics which is based on probability, dice. So he said about this, these were the comments, but at the end it came out that this is the very fundamental thing. Classical mechanics is just a corollary of this thing, is just the assumption when you put some conditions on mass, then you will, on the size, you will get the results of classical mechanics. So this was tell the quantum mechanics. Now you know here that we are having both m and v. M is very down here, the tiniest particles. What about v? V is also here, means when you consider electron in material, it is much less than the speed of light, but some free particles, they are having their speed close to the speed of light. You are dealing with the photons which are exactly going with the speed of light. So relativistic quantum mechanics, when you consider very high speeds, then quantum mechanics converts into relativistic quantum mechanics. And the reason for that was the another mechanics which you call the theory of relativity or special relativity. You know that on mass, when the mass was becoming small, your realistic mechanics failed and probabilistic mechanics came in. Now what about V? That what if V goes very high? Then what will happen? Whether this mechanics will work or this mechanic will not work. And let's consider that when we consider the issue which this was the special relativity was after Albert Einstein. He was not only he was the founder of it, although the equations were derived by Lorentz. So Lorentz has already worked out those things, but the main formulation was after Einstein. And here you know that in classical, when we consider classical electrodynamics and the Maxwell equations are there, let me write the Maxwell equations, that the divergence of electric field is the charge density by epsilon naught. Magnetic field does not diverge at all. The curling electric field is generated when you vary magnetic field and time, and curling magnetic field is generated when there is a constant term mu naught J. This was the setup before Maxwell. Although Maxwell was the one who gave them equation forms, who wrote these equations, like this is Faraday's law, and Faraday never wrote an equation. He was just having observations. But Maxwell was the one who wrote the set of these equations. Maxwell wrote around 20 equations. His student converted them into 10 equations, the Oliver Heaviside, and now we are having it this form. There is another equation, the continuity equation, which we will also discuss one by one. Divergence of J is equal to minus curly rho over curly T. Continuity equation, but this is not in Maxwell equation. Maxwell equation are these, but these equations were incomplete. And when Maxwell corrected this one, mu naught epsilon naught curly E over curly T, then the whole picture became cleared from this one. And that was the reason that he derived a wave equation, and he said that there is a big spectrum of electromagnetic waves in which visible light is one, and optics and electricity and magnetism, they all merged into each other. Before here, for this one, you were having electricity and magnetism. When Faraday did his work, he said that electricity can't be separated from magnetism, or magnetism can't be separated from electricity, and he termed it as electromagnetism. And after the work of Maxwell, magnetism was gone and it was all electrodynamics, charge and motion. So if we call it a magnetic field, it is actually a varying electric field and nothing else. Because there should be field, field should have a source, and that field will have a force. So the source of both of them was charge, so that's why it is electrodynamics. Although Maxwell, you know that Maxwell didn't know about the electrons and protons. He was considering charges only. He did two mistakes, you can say, or there were two not right things. The one, he corrected the Ampere's law, but he gave it a wrong name. So the name wasn't right, but the term was right, the equation was right. And another thing was, when C is equal to this much, which is 2.9979 10 raised to the power 8 meter per second, the speed of light, or the speed of all electromagnetic waves, a big spectrum from radio and microwaves to gamma rays, all this spectrum, this is an electromagnetic world, they are all traveling with this constant speed. So there was a big question with respect to what this light is traveling. Because from the Galilean and the Newtonian mechanics, it was all the concept of relative motion. If I'm moving, you are saying that I'm moving, then I'm moving with respect to you. I'm moving with respect to the stationary floor, this room, all are references. But if you remove all the references, and let's say me and Musa are in the universe, there is no reference at all, then he will be saying that I'm moving and I will say that he is moving. But there will be no rest at all. So the motion is relative. It is not, you can say, absolute. It is with respect to something. The concept of motion till that time was due to this. But when he was asked that it is moving with respect to what, then he proposed a hypothetical medium which is called ether, the theory of ether, that the light is traveling with respect to ether. But then in 1931, Michelson and Morley, with their interferometer, proved that there is no ether at all. And then it was a gap. No one was able to explain this mystery, that if it is a motion, then it is motion with respect to what? And Albert Einstein came in and he said that when you derive this equation from the Maxwell equation, do the Maxwell equation put any restriction that it is to be a motion relative to something? And the answer was no. Then he said, why you are in search of a reference then? It is an absolute motion. It is irrespective of any frame. It is not depending on the source. It is not depending on the observer. It is independent of any frame. This is an absolute motion. Just like, consider that this is body A and this is body B. Body A is going in this direction, let's say with 20 meter per second, and body B is going with 30 meter per second. Now with respect to body A, how much is the speed of body B? It is 10 meter per second. But with respect to body B, what is the speed of this one? It is minus 10 meter per second, or 10 meter per second in the other direction. If there is a person who is stationary here, with respect to him, he is traveling at, body A is traveling at 20 meter per second, body B is traveling at 30 meter per second. But if that frame is also traveling at 10 meter per second in this direction, I mean, there is no stationary frame at all. So what he will say? He will say that this body is traveling at 10 meter per second in this direction, and this body is traveling at 20 meter per second. So none of the reading is correct, because when all are traveling, these readings are not correct, they are relative. Now what if the situation becomes very, you can say, high speed, and you say, because we were adding and subtracting these speeds. Now let's say a rocket is going, a shuttle is going at a very high speed, and let's say it is 0.6 c, very high speed, and a person here switches on a torch, and the light from that torch, you know that it will move at a speed of light. So what will be the net speed of that light? Because 1c plus 0.6c, it will add up according to this principle, right? And it will become 1.6c. If the rocket is going this way and the torch, a person switches on in this way, then 1c here and 0.6c here, sorry, 0.6c here, because this is the rocket, and 1c is here, this is going in this way, right, in this direction. So now what will be the speed of light then? It will be 0.4c, because they are going in opposite direction. But, or you can consider, out of this frame, one shuttle is going this way, another going this way. Now all observed that this speed comes out to be the same as c. All measured the same speed, irrespective of this situation. And that was the reason that Einstein put forward, that speed of light is an absolute speed. It is not a relative speed. It is irrespective of either the motion of observer or the motion of the source. Clear? And he just focused on this thing, motion. You know, motion, it is space over time. Motion is space over time. Speed. Motion is speed. So he said that this thing is absolute. This is not relative. Clear? This is absolute. And it is independent of both the source and the observer. And he, with the help of this, he just laid a foundation of this thing, of special theory of relativity. Because there were some problems. Those problems, one was this problem, which he resolved. Another problem was the elementary particles. You know that if we consider the elementary particles, you know how much time light takes to reach from moon to the earth? 1 second. In 1 second it reaches to the earth. If you consider the light from sun, and it takes 8 minutes and around 20 seconds. Now, if some particles are created inside the sun, some elementary particles, and we receive those particles on the surface of earth, those elementary particles. And we know that the lifetime of those particles, like when they are generated and they just disintegrate, they just vanish. If it is, let's say for example, 4 minutes, then whether those particles will be able to reach Earth? No, because halfway they will lose their life. But it was something strange that those particles created in the sun and observed on the Earth's surface with that lifetime. Like in, so it means that the time has dilated, and there was no concept of time dilation in the classical mechanics, right? It was a concept of the special theory of relativity, the time dilation, the length contraction. Length is space, this is time. So when you consider time dilation, then those particles can reach Earth. Otherwise, they cannot reach. They will disintegrate earlier than reaching to the Earth. So that problem was resolved with this one. And another of space. In classical mechanics, you know, we are having this classroom. This classroom is in the department in the Peshawar city. Peshawar is in KP. And then we are having Pakistan, and then the subcontinent, and the whole world, the globe. Then we are having our solar system, and this another system, and this galaxy, and many galaxies, and the whole cosmos. If you remove everything, the visible and invisible both, like the matter and the energy, dark energy, and that you remove everything, whatever remains is called space. एक बंदे से किसी ने पूछा कि आपको पता है कि कायनात जो है ना वो फैल रही है, The universe is expanding. उसने कहा मुझे इसकी फिक्र नहीं है कि ये एक्सपेंड हो रही है, मुझे तो उस चीज़ की फिक्र है कि ये एक्सपेंड किस चीज़ में हो रही है. Like in what it is expanding means there is something in which it is expanding. That is called space. According to Newton, this space is absolute. This is not responsive. It is static. But according to Einstein, it is not absolute. It is responsive. It is responsive.